us to another episode on SUG 12 exams. So in this episode we are looking at the 2019 Science Paper 1. So let us look at question C1. A spling with its upper fixed end hangs vertically alongside a meter lure. The lower end of the spling gave the following readings in table C1.1 when various masses were hung from it. So we have mass in kg, readings in centimeter, then we have applied force in newtons. Then we have extension in centimeter. State Hooke's law. That's question A. So Hooke's law basically states that the force applied to the spling is directly proportional to its extension, provided it does not pass the elastic limit. So basically, ideally, what it says is, if you have applied force is basically directly proportional, so we can have a constant then to the extension. This is what it tells. So if we apply more force, then extension will also increase, as long as we don't go beyond the elastic limit. So that's what it implies. A force applied to a spling, so force applied to a spling is direct proportion to its extension, provided we do not pass the elastic limit. So if you can't remember the word, just remember this formula. This formula will help you to remember how to explain. So applied force is direct proportion to extension, okay, as long as we do not pass elastic limit. So once we pass elastic limit, this proportionality will not work. Then B, copy and complete the table for the values of applied force N and the extension in centimeter produced. So for B, so applied force F is equal to weight, which is equal to basically mass times gravity. So what you notice here is, for the first one is basically the mass is 0. Remember, gravity is 10 Newton per kg. So it will be 10 times 0. We end up with applied force to be 0. On the second one, when mass is 0.02, then weight will be 0.02 times 10. It will be basically 0.2. Then on this one, it will be 10 multiplied by 0.04, so it becomes 4. So similarly, like that, then we have that until the last one, which will be 1 kg. Now this 1 kg, this is an error. It's supposed to be 0.1 kg. You multiply by 10, so it will give you 1 Newton. So basically, this is what is happening. Then we go to extension. So extension will be basically Li, then minus the length of the spling before we loaded in mass, or we applied any force. So for the first one, it will just be 10 minus 10, which will be 0. We are seeing here. The second one, it will be basically 12 minus 10. Now remember, this is the 10. Okay, so this formula generally becomes Li minus 10, because this will be fixed. The length before, which is the reading before we apply any mass. So it will be, on this one, it will be 12 minus 10, which will give us 2 centimeters. So here we have 2 centimeters. The next one, it will be 14 minus 10, it will be just 4. Then the next one, it will be 16 minus 10, it will be 6. Then 17 minus 10, it will be 7. Then 17.5 minus 10 to be 7.5. So basically this is how you complete this table to get these 4 marks and 1 mark. Then we go to C. Draw a graph of applied force against extension on graph paper. So applied force will be y, then extension will be x. Then remember the first one is the y axis. So once we do that, we can go to the graph paper and plot this information. So as you see on the graph paper, this graph has been written appropriately to ensure that it's easier for us to do. So make sure that you label the x-axis is basically extension in centimeter, then applied force is in newtons. Then once you do that, make sure that you use the same scale. So as you will notice, the centimeters are increasing in intervals of 1 unit, from 0 to 1, 1 to 2, 2 to 3, then 3 to 4, all the way up to 8. Why 8? The maximum here we have is basic extension is 7.5. So the highest thing we can go is 8, because we don't have any 10. Then similarly, applied force is increasing in the interval of 0.1 unit, from 0.1, 0.2, all the way up to 1 newton. Then when we do that, we can start plotting this on the graph. So we have 0,0, which is the first point. So remember, when you use 0,0, if it's there, if it's not there, you don't start from there. Then we have applied force when it's 0.2, extension is 2 centimeter. So 0.2, 2 centimeter is basically this point. Then we have 0.4, 4 centimeter. So 0.4 is here. So this is where they're meeting. Then we have 0.6, 6 along 0.6, 6 centimeter. We have that. Then we have 0.8, 7. So along 7 we go to 0.8. So we have somewhere here. Then we have 1 Newton, 7.5. So 7.5 is halfway between 7 and 8. So we are going to have to be somewhere basically here. Okay, so this is what is happening. So now you can join these points. So you notice that from here to up to this point, this is a straight line. Then this start bending upward up to here. Start bending upward like that. That is what is happening. So this is how the graph will look. So basically, this is how you get these 4 marks that we've already gotten by completing the table, and this by plotting the graph. Then D on the graph, show the elastic limit. So at what point does the Hooke's law stop applying? So at what point will the applied force to the spring will no longer be proportionate to its extension? So you notice exactly on the graph basically is when we reach this point. So after this point, this no longer, the proportionality is no longer obeyed, because despite increasing the applied force, the spring will not extend in proportionality. So that tells us we've passed the elastic limit. So basically, this is we shall call this to be elastic limit, EL, elastic limit. So beyond that, we have gone above elastic limit. So basically, this is how you answer this question to get the 10 marks. Let us look at C2. two lamps S and T of resistance 200 ohms and 300 ohms respectively are connected in a series with a 240 volts mains as shown in figure C2.1 below. A. Calculate Roman numeral 1 current at point V, then Roman numeral 2 potential difference across lamp S. So what we need to know is when you're dealing with a series circuit, in a series circuit, the current in that circuit is the same everywhere. So basically, from the fact that voltage is equal to resistor times current, to find current is basically we divide by resistor everywhere. We have voltage divided by resistor. Then the resistor in the series circuit, the resistor is just basically the summation of individual resistors. So in this case, it will be resistor 1 plus resistor 2, which is different from parallel. So it will be 200 plus 300, which gives us basically 500 ohms. So based on that, we can get this formula here and solve for current. So the current at V will be the same as the current in the entire circuit. So current, so this is Roman numeral 1 is equal to basically voltage is 240 divided by the current of 500 ohms. This will give us a 0.48 amps as our current. Then let us move to Roman numeral 2. So Roman numeral 2 is potential difference. So if you look at potential difference, it will be basically shared among components in the series circuit. While under parallel, it will be basically the same. And what will be shared among the components is it will be basically current. So current basically will increase as more components are added under the parallel circuit. But under basically the series circuit, it will be the same across the circuit because of the arrangement of the circuit. So we need to find potential difference across lamp S. So across lamp S, basically we know that potential difference, which is voltage, is equal to current times resistor. So our current is 0.48 multiplied by resistor, which is 200 ohms. When we multiply these two, we are going to end up with 96 volts out of the 240 volts. So basically that's the potential difference across lamp S. We move to question B. So question B says, draw a circuit diagram showing resistor S and T connected in parallel. So connected in parallel. So if they're in parallel, what we need to do is basically we can draw this circuit that it has maintained this to be basically the 240 volts. So if they are in parallel, what we can do is draw here. So this will be basically this will be S, then we can draw another one here and put it to be T. Then what you notice here in this case, let me just rub in the middle so that it looks neater. So we can call this to be S, then this to be T. So what you notice in this case, and this will be S is 200, then T is 300 ohms. 300 ohms as our resistor. Then here we are going to have this as the voltage. We draw it the way it is, we maintain, then this will be 240 volts. So this is how the parallel circuit would look. So this is what you need to do to get the 1 mark. Then C, using the diagram in 2B, calculate the current through lamp S and T and Then Roman numeral 2, we need to calculate the total resistance of the circuit. So basically what you notice in this case, in the parallel circuit, the potential difference will be the same across all the components. So we can use that fact to answer B by to answer C. So now what is happening now is this is now in parallel, then this is another one. Remember that we've drawn from here. So now we use the same one to do now in this case to find the current at S. Remember the potential difference is the same across. So we need to find current. So current is equal to basically voltage over resistor. Then voltage is the same now in parallel. Voltage is 240. So we have 240. Then we divide at S. What is S? Is 200 ohms. So we divide by that. Then we're going to end up with basically 4 into 24. This is basically 6. 4 is 5. 5 into 6 is 1. Remainder 1, so it's 1.2 amps. So 1.2 amps will be the current in basically through lamp S. Then which is Roman numeral 1, C1, then C2. So this is C2. Then we'll do the similarly, current is equal to voltage over resistor. So in this case we have 240, but potential difference is the same, divide by 300 ohms. Then we divide that and that. Then we have 3 into 24 is basically 8. So we do 10 into 8, we get 0.8 amps as through T. So through T is basically 0.8 lamps. So this is still C1. So now we move to C2. So C2 is asking us to find the total resistor of the circuit. So total resistor of the circuit is basically R1 multiplied by R2 over R1 plus R2. That's basically, then what this tells us, we are going to have basically 200 multiplied by 300 over basically 200 plus 300. This will give us basically 200, rather not find this big number, 300 multiplied by 200 over, we add this to it will be 500. So in this 500, I can easily basically cancel the zeros, 0, 0, then I have 2 multiplied by 3, which is basically 600. So 600 divided by 5, so 5 or 5 into basically 20 is basically 40. Okay, so I have a 40 there. Then 40 times 3, I end up with 120 ohms. So 120 ohms is basically the combined resistor of this circuit. Then we go to question D. So question D basically give 2 reasons why lamps are preferably connected in parallel in ohms. So why are they in parallel? Normally in ohms we connect them in parallel. So the first reason is basically is for the purpose that if one component, so what we notice here is under parallel, if one component, let us say T is bent, if T is bent, potential difference will be able to pass through the circuit and still S will be on. That's one of the advantage or the reason why this is normally used in the homes. Then number 2, basically what you notice is each component received voltage supply. So regardless, each component will receive the same potential energy or voltage supplied to the circuit as long as they are in parallel. If they are in circuit, the potential difference will be different, and the fact that if one of these is bent, then the entire circuit will be off. So what we discover is in the home, if one bulb is bent, the entire house becomes dark, which is a disadvantage. Can one work that even if one bulb is bent, the other will still be on if you use the parallel circuit. So those are the 2 reasons that the lamps are preferably connected in parallel in ohms. So basically, this is how you answer this question to get the 10 marks. Let us look at question C3. Figure C3.1 below is a diagram showing a bowling ball as it rolls down the incline for 5 seconds before reaching the horizontal ground. The changes in the gravitational potential energy of the bowling ball as it rolls down to the horizontal grounds are shown in table 3.2 below. So we have time elapsed in seconds, then we have potential energy in joules. So time is ranging from 0 to 5 seconds, then potential energy from 9 to 0 joule. Question A, state the law of conservation of energy. So the law of conservation of energy states that energy can be changed from one form to another but cannot be created or destroyed. So energy basically can be changed from one form to another but cannot be created or destroyed. That's what the law of conservation states. Then we go to B, using the values in table C 3.2, draw a graph of potential energy against time. So what we need to do is to transfer these variables to a graph. So without wasting much of your time, I'm going to label the graph, then you join me in the other section once I label it, so that we don't waste much of your time. Okay, so we have done the graph. So we've labeled the x-axis to be time elapsed in seconds, then the y-axis potential energy in joules. So what is needed now is to transfer these values time elapsed against potential energy on the graph. So the first coordinate is 0,9. So when time is 0, potential energy is basically 9. So it's at that point. Then when time is 1 second, potential energy is 7.2. So 1 again is 7.2 is somewhere here. Then 2, 5.4. So when time is 2 seconds, the potential energy is 5.4. So it's just somewhere 1, 2, 3, 4, just somewhere here. Then when time is 3 seconds, potential energy is 3.6. So 3.6, just above 3.5, which is somewhere here. Then we have 4,1.8. So 4,1.8 just below here. Then we have 5,0, which is at this point. Then after that, use your ruler to join these lines to make a straight line, which will be something like this. So I'm just using a rough sketch, but it will be a straight line. So this is how it will look. Once it looks like that, then you finish, then you get the 4 marks. Let us look at C. Calculate the height h of the inclined plane. This one, when the potential energy was 900 joules, if the mass of the ball was 900 grams. So the mass here, this is 900 grams. So we need to find the height. So let us go back to where we have space and it's bigger. So remember, this is 900 grams. So we know that potential energy or gravitational potential energy is given by mass times gravity times height, where gravity is basically 10 Newton per kg. So we need to convert this to kgs, which is 900 grams. To convert to kgs, we divide by 1000 because there are 1000 grams makes up 1 kg. So we end up with 0.9 kg. Then we know that the potential energy we are told was what? 900 joules. So what this tells us is basically 9 is equal to basically mass 0.9 kg multiplied by gravity, which is 10 kg per Newton. Remember this, the kgs will cancel because we're multiplying, then multiplied by h. So what we have is 9 is equal to 0.9 times 10 is 9h times h, which is 9h. Then we divide by 9, divide by 9. So we know 1 is equal to basically h. So this one is in meters. Remember, height is measured in meters. So this is 1 meter. So basically, this is how you answer C to get these 3 marks, which is 1 meter. Let us move to basically D. Using the graph, estimate the kinetic energy of the bowling ball at time 2.5 seconds. So let us use a different color. So 2.5 seconds is somewhere here at the middle. So the middle of 2.2 and 3. Then we need to move up there and check at this point. So it's somewhere here. And this is exactly halfway, or between 5 and 4. So if you use a straight ruler, it will be like that. So you check, this is 4.5. So this 4.5 is potential energy. Now remember, as the ball is falling, the potential energy is being converted to kinetic energy. So if you are remaining 4.5 potential energy from the initial 9, so what it means is kinetic energy at this one, which is number 1, kinetic energy will be basically 9 minus the potential energy available. So it will be basically 9 minus 4.5, which gives us 4.5 joules as the remaining kinetic energy. So at 2.5, half a time, half of the potential energy would have been converted to kinetic energy. We move to D. So D2, I'll use this one. So at D2 is 4 seconds. So we come to 4 seconds. So 4 seconds is exactly at this point, which is exactly, we have it on the table. So we come here, it will be basically 1.8. So 1.8 is the potential energy. So using the same principle, we have kinetic energy. In this case will be 9, the total available at the beginning, which is this one, minus the potential energy available now. So we are going to have basically a 9 minus 1.8. So 9 minus 1.8, basically what it tells me is we are going to remain with 7.2 of kinetic energy as our answer. So at 4 seconds we have 7.2 kinetic energy because of conversion. At this point we are only remaining with 1.8 of potential energy. Then it means the other energy has been converted to kinetic energy. Remember, the key is the law of conservation. So if kinetic energy is only 1.8, then potential energy would be 7.2 here. So once potential energy becomes 1.8, then kinetic energy has now become 7.2 because the other 7.2 to give us 9 has been changed to kinetic energy from potential energy. So that's the principle we are using here. So basically, this is how you answer these questions to get the 10 marks.